Okay, now it's loading. Now it's recording for real. So we have 1,3-butadiene, and so how many atomic orbitals do we see here? Four. Cool. So each of these red orbitals is an atomic orbital. And then someone said, why would the electrons be in the opposite position? So like on the top and on the bottom. That just has to do with orbital theory. So as far as you guys need to know, it's not really important or relevant. Just that's how we depict it in higher level chemistries because of steric effects and the way p orbitals are aligned and everything. So yes, this has 4 atomic orbitals, and I'm going to abbreviate that as AOs. And how many molecular orbitals do you think that correlates to? Okay, so it's approximately 50-50. Some people are saying 2, some people are saying 4. And this is actually kind of a trick question because it's exactly the same. So the number of molecular orbitals and atomic orbitals in this case are going to be the same. So we're going to have 4 MOs for molecular orbitals. And so now, how many pi electrons do we have? What do you guys think? 4, cool. And the reason for that is each one of these electrons that contributes to a double bond is considered a pi electron. So we have 4 pi electrons. Sweet. So that's the first part of molecular orbital theory for 1,3-butadiene. And someone actually asked a really, really great question, which is what I was about to segue into. So we have something called the ground state and the excited state. And this stuff that I have right now is going to be the same for the ground and excited state. So this won't change. But all of our other values will be different. So I'm going to specify ground versus excited. And I'll go into more of what the difference is in a moment. But we're just going to first focus on ground. Pretend you don't even know what the excited state is. So when we're drawing the molecular orbital energy diagram, it's going to be one line for each orbital. So since we have 4 orbitals, we're going to draw 4 lines, like so. And each of these lines is going to correlate to an energy level. So let me actually just change the color so you guys don't get confused. So each of these lines correlates to another energy level. And we're going to name those pi 1, pi 2, pi 3, and pi 4. That's just how we name them. He could also give you this figure, this symbol, I believe. That means the same thing. I just forget what those are called. I think it's psi. Same thing, doesn't matter. So then we go into filling up these orbitals. So since we have 4 electrons, it will go 1, 2, 3, 4. And please remember that you have to fill up 1 orbital in order to go up to the next one. Or excuse me, 1 energy level before you go up to the next one. And the reason for this is because, and I'm going to draw this, don't freak out. Just let it happen for a second. So for each orbital, we're going to represent it here next to the line. And for the lowest energy level, they're all going to be filled in on the same side. So the lowest energy is when they're all filled in on the same side, like so. Every time we go up one energy level, we're going to add a node. And all a node is essentially like a line between the orbitals. And at the node, you flip which side is filled in. So now we have half of them pointing up, half pointing down. So then when we go up one more energy level, we know that we're going to have 3 nodes present. And so it'll look like so. Or 2 nodes present, but 3 different flips. And you'll see what I mean in a second. So the first one will stay up. This next 2 are flipped down, and the last one is flipped back up. So we have 1, 2 nodes, but we flip 1, 2 like that. In the last state, every orbital will have a node in between it. So we have 3 nodes, and so we flip every single one. So it would be up, down, up, down. This has to do with the flow of electrons through the system, but you don't need to know that for Orgo 2. If you're interested in it, though, I'd be happy to share a cool diagram with you later, but we don't have to spend time on that if you don't care. So one thing you should notice is that 2 of our energy levels are full and 2 of them are empty. Does anyone know how we could possibly name these different kinds of orbitals? Yes, someone said it really fast. Nice. So we have bonding versus antibonding, and someone said HOMO and LUMO. We'll get to that in just a second. First, you have to understand what bonding is and what antibonding is. So the bonding orbitals are just going to be the ones that have electrons in it, and antibonding will be the empty ones. So pi 1 and pi 2 will be bonding. And notice that in this case, the number of bonding and antibonding are going to be equal. That is, sorry, I can't write and speak at the same time. That is important to note because in this class, the number of antibonding orbitals will always equal the bonding orbitals. Another way for us to name or like keep track of what's what is antibonding orbitals are going to have a star. Someone asked the difference between an orbital and an energy level. So I kind of almost use them synonymously, but an orbital is just what is actually on the molecule that's holding the electron. So that's just an area in space where an electron is located. And the energy level is just kind of a qualitative measure of how much energy the electron holds in each level. Kind of. That's not the best explanation, but that's the best I can do to like simplify it. Does that sort of kind of make sense? Sort of, kind of. Okay. So someone said, can you have an antibonding sigma orbital? Yes, but for this class, it's kind of complicated. That's like an Orgo 1 thing. I recommend going to the textbook and looking at the bonding diagram that they have because it's interesting. But as far as Orgo 2 goes, it's much more straightforward and simplified. So you just have to focus on the pi bonds. And so the pi orbitals. So yes, we did bonding, we did antibonding. And so now we're going to compare the ground state, which is what we just drew, to the excited state. So the excited state is just when we put enough energy into this molecule that one of the electrons jumps up an energy level. So I am actually going to go ahead, and since I'm not on a whiteboard, I don't have to redraw all of this. I'm just going to move it here. Actually, I really hate how that looks. I'm not going to include the names because they're exactly the same. The only thing that's going to change is the place of one of those electrons. So one electron is going to jump from pi 2 to pi 3. Now that we've drawn in all the electrons, we have to cover an important vocab term, I guess, that someone mentioned before, the HOMO and the LUMO. So I'm going to define those right down here. Does anyone know what the HOMO stands for? And what the LUMO stands for? Yes, so it's the highest occupied orbital, and the LUMO is the lowest unoccupied. Exactly. Sorry, I stopped writing halfway through the word. I was reading the chat. Exactly. So the HOMO is going to be the highest energy level that has an electron, and the LUMO is going to be the lowest one that is empty. So in the ground state example, which one, pi 1, 2, 3, or 4, is going to be the HOMO? 2. Awesome. So I'm going to write it right here. And so which one is going to be the LUMO? And I actually decided that looked ugly, so I'm going to write it on the left side. 3, exactly. So since that is the lowest energy level that is empty, it is going to be the LUMO. And since this is the highest energy level that is full, it is going to be the HOMO. So now in the excited state, which one is going to be the HOMO? Okay, and what's going to be the LUMO? Haha, I tricked you. Trick question. I'm so glad you fell for it, and I'm sorry that I tricked you. But essentially, a really stupid thing that chemists do is they like to make things not make sense. So I just told you that the HOMO is the highest occupied and LUMO is the lowest unoccupied. So then you're like, duh, this is now the highest occupied. This is the lowest unoccupied. Except when we go into the excited state, we are not going to change the namings. So this is a temporary state. The electron jumps up and then comes right back down. So we are not going to change the HOMO and LUMO. Pi 3 is still the LUMO, even though there's now an electron in it. And pi 2 is still the HOMO. Don't ask me why this is the convention. It just is. Any questions? Okay, someone said they're a little bit confused on how to fill out the chart. Yeah, I'm going to go back up to that in just 1 second. Does anyone have any questions just on what we drew and what we talked about so far? I'll give you a couple. So LUMO and HOMO doesn't change. Exactly. So between the ground and excited state, the only thing that changes is one electron. So you're actually not going to change the naming of HOMO and LUMO. And so, yeah, this would still be the LUMO and this would still be the HOMO. Which is weird, but it's just what they tell us. So if we go back up here and we go to the chart that I gave you guys, I am going to ask you questions. And I want you to just give me the numbers in the chat, please. So what did we say the number of atomic orbitals were in our drawing? 4, absolutely right. How many molecular orbitals did that transfer to? 4. How many pi electrons? 4. Sweet. And does that change from ground to excited? No. So I'm just going to go ahead and also fill that in here. So for some reason I wrote bond instead of bonding, which I think that was just to save space. But how many bonding orbitals did we have, aka bonding energy levels did we have? 2. How many antibonding? Again, 2. Sweet. Okay, so how many non-bonding did we have? 0, because we never talked about non-bonding. Awesome. So how many bonding electrons did we have? I didn't explicitly say that, but I want to see if you guys... Okay, cool. So people were saying 4. And so what that means is how many electrons we had in bonding orbitals. So in this case, it was 4. And so by that logic, how many antibonding electrons were there? 0. Perfect. And so if we have 0 non-bonding orbitals, how many non-bonding electrons can we have? 0. Sweet. Okay, so how many electrons did we have in the HOMO? 2. How many did we have in the LUMO? 0. Perfect. All right, so now these answers are going to change a little bit once we get into the excited state. So did the number of actual orbitals and energy levels change? No. So these first few columns will stay the same. But now in the excited state, if we zoom on down, how many electrons do we have in bonding orbitals? 3, exactly. So if we zoom back up, how many did we now have in antibonding orbitals? 1, exactly. And we still have 0 in non-bonding because we don't have any non-bonding right now. So how many electrons did we have in the HOMO? And I'll zoom down so you guys can take a look. So a couple people originally said, does it stay the same? Well, you tell me. So if this is still the HOMO and this is still the LUMO, while the naming stays the same, the number of electrons does not. So now instead of 2 and 0, we have 1 and 1. And bam, you just did molecular orbital theory for our first example. Any questions so far? So what is non-bonding? We will go into that in just 1 second. It's something that's specific to when you have only 3 energy levels. Cool. Okay, so let's go to the next one. And before I even start, I'm going to go ahead and make my life easier. And I'm going to just duplicate this so I don't have to redraw the same exact thing a bajillion times. But don't write anything down yet because I want to fix it to be accurate. So now when we are talking about the cation or anion or anything like that, or radical, the thing that's going to change is primarily, sorry, 1 second, I really can't write and think at the same time. Okay, we're good now. And I think someone had a question, so let me look at that real quick. Okay, so someone said that they thought that for the excited state, the bonding molecular orbitals would be 3 and the antibonding would be 1. So that's a good, like a logical way to think. But like we said before, the naming for these orbitals is not going to change. because even though the one electron moves, the orbitals themselves don't change. So instead of changing this to a bonding orbital, you're actually just going to change that there is now one electron in the anti-bonding orbital, which is weird, but for some reason that's how they keep it. And if you think about it, it kind of makes sense because, again, you're not changing the container, you're just changing what's in the container, if that makes a little bit more sense. So now we're going to do the exact same thing, but we are going to do it for the anion, the cation, and then the radical. And I'm just going to zoom up to see which order I put it in. So, okay, cation first. That's easy peasy. So when we have a cation, what charge do we have? Positive, exactly. So if we have a positive charge, that means we have a p orbital, but it is empty. Completely empty, nothing in it. So how many atomic orbitals do we have in this case? 3. Cool. And so how many molecular orbitals are there? 3. How many pi electrons are there? 2, exactly. Perfect. So when we move on to this drawing, and let me just erase, whatever, start over. So now we only have 3 orbitals in our little drawing here. But the most interesting part, I think, is that the middle energy level only has 2 orbitals that we're going to draw. And it's weird, but trust me, it'll hopefully make sense in a second. So as we said, the bottom energy level is going to have 0 nodes. So they're all going to be filled in on the same side. And then on the next one, we know that it's going to have 1 node right here. And so one is pointing up, one is pointing down. And then 1 more node for the one above it. So we get bam, bam, filled in, up, down, up. And the reason that there are only 2 on the second energy level is because that node is actually going to be formed right on the second orbital, or the middle orbital, I should say. And that means that there will never be any electrons in that second orbital, so we're just going to essentially ignore it. You don't have to necessarily understand why that is. Just know that that's a thing. So if we have 2 electrons, we're only going to fill up the first energy level. And so if that is the case, which one of these will be our bonding orbital? And then someone asked, when will the number of atomic orbitals and molecular orbitals be different? In this class, essentially never. So in this class, they're always going to be the same. So with that being said, you guys were right. This is bonding. And since there is only 1 bonding orbital, how many anti-bonding orbitals can there be? We're getting some split answers, but the majority is 1, and that is the correct answer. And the reason for that is, like we said, essentially bonding and anti-bonding are like a couple. They have to come in a pair. So the number of bonding has to equal anti-bonding. So that leaves us with the one in the middle. What the heck is that one? Can you guys take a guess at what we could call the one in the middle? Non-bonding, exactly. Perfect. And the reason, again, it's called non-bonding is because it's really weird. It's this layer in between the bonding and anti-bonding, and it has that weird node in the middle that, I forget what the word is in English, but it essentially like covers up one of the orbitals so no electrons can be found there. Any questions? This is usually where I lose everybody because they're like, what the heck is non-bonding? Any questions? Sweet. And then, sorry, I got a bunch of things at once. So, yes, so it's just the node is covering one of the orbitals. Hence, there is a split in the middle, and one of the orbitals won't have any electrons in it. So, yes. And then, okay, so I don't know how old Dr. West's recordings are for the lecture, but I do want to say something about this before we go on. So, one semester, Dr. West was saying some different things about molecular orbital theory, and he was saying something weird that I wasn't familiar with, and it was kind of contradictory to the textbook, but he said that that was just what it was for now. I believe in the videos he explains it the way I did and the way that I see the textbook explain it. So you guys shouldn't have any contradictory information here, but I will watch it again just to make sure because I don't want you guys to get confused. If you have no idea what I'm talking about, ignore what I just said. Cool. So in the excited state, all that's going to happen is one electron jumps up. So please tell me which one of these will be the HOMO. Yes, pi 1 is the HOMO. And so which one is, the LUMO? 2. Sweet. So I will let you guys just have this up here for like a few seconds, and then we're going to go up and we're going to fill out the table for this example. So someone asked, why isn't number 3 the LUMO? And so that's a great question, that's a great question because of what we talked about previously, but we're just going to talk about the lowest energy level that is empty. So let's ignore the excited state, only looking at the ground state. The lowest energy is pi 2, that is empty. So that's why that one would be the LUMO. Cool. And then someone asked, so the middle p orbital is non-bonding and it has no electrons. So yes, the actual, you know what? As far as this class goes, yes, that is a sufficient explanation. You are correct. All right, so let's zoom back up here. And we're going to do like a rapid fire for the first couple. So how many atomic orbitals? 3. How many molecular orbitals? 3. How many pi electrons? 2. And then I saw that there was a question. I'm not ignoring you. I'll just go back to it in a second. So how many bonding molecular orbitals are there? 1. How many antibonding? 1. How many non-bonding? Shocker, it's 1. Cool. So is there any difference between this and these in the excited state? No, so that's going to be exactly the same. Now what's going to change is the electron distribution. So in the ground state, how many electrons are in bonding orbitals? 2. Sweet. And then how many are in antibonding? 0. How many are in non-bonding? In the ground state? 0. Cool. How many are in the HOMO in the ground state? 2. And in the LUMO? 0. Sweet. So now in the excited state, how many electrons are in the bonding orbital? 1. How many in the antibonding? Still 0. Cool. How many in the non-bonding? 1. Perfect. And so how many are in the HOMO? 1. And in the LUMO, can we guess? 1. Sweet. I don't know why I have the hiccups today. Excuse me. Cool. So you finished another one. Yay! Any questions before we go on to the next one? So I just, looking at it, realized I put the anion before the radical. So I'm actually just going to cover it in the reverse order. So I'm going to cover the radical first and then go into the anion. And so someone asked, I think this was the same question as before. If not, ask it again. Is the LUMO and HOMO the same for the ground and excited state? Yes. The HOMO and LUMO are not ever going to change for the excited state. So whatever we label it in the ground state, it will stay the same. Okay. So give me like 2 seconds while I paste this again. Delete. This is so much easier, but also so much more difficult on an iPad rather than a whiteboard. It's very interesting, for sure. Okay, so one thing I want you guys to notice, first of all, is when we have the radical, it's going to look like this, and the p orbital at the end is just going to have one lone electron in it, again, because that's the radical. And since there are 3 orbitals, this little diagram that we drew on the side will be exactly the same. So that isn't going to change. The only thing that will change is the number of electrons. So that's what we're going to go ahead and cover. Any questions before we get started on this one? And so, yes, we're doing the 4th one just because I put it in a weird order. And just so nobody gets confused, I'll go ahead and label these. So this is 1,3-butadiene. This is the carbocation. Now this is the radical. And we will do, sorry, I feel like I had a stroke. This is the radical, first of all. And then we will do the anion last. Sorry for my little absent brain. So, how many atomic orbitals do we have in this drawing? 3. Cool. So how many molecular orbitals do we have? 3 again. Sweet. And how many pi electrons do we have? 3. Cool. So that's what's different. And so now, 1, 2, 3. Ooh, that's really weird, right? And so, oh wait, first someone said 2, and I totally see why you would think that, and I'm actually glad someone said 2, and that's because usually people don't think of the radical as being a pi electron, which is something new for a lot of students in Orgo 2. So I want you guys to realize p orbitals are not just double bonds. So a p orbital includes double bonds, cations, anions, and radicals. So I totally see where you were coming from. But in this case, we're going to count all the electrons that are in radicals, double bonds, and anions. So now we have a really, really weird case, right? So the bonding and antibonding orbitals are going to stay the same. Non-bonding will stay the same. But the HOMO and LUMO are going to change because now we have an electron in pi 2. So what is the HOMO? Pi 2, exactly. And so what is the LUMO? Pi 3. Sweet. And so now in the excited state, the bottom energy level is going to stay the same, but that one from pi 2 jumps up to pi 3. So it's an extra weird looking thing, but that's actually what we're going to be stuck with. So any questions thus far? And let me actually put the star here because I forgot to do that. So yes, someone would like me to explain HOMO and LUMO again. I would love to. So essentially, the HOMO and the LUMO are just a way to label the ground state, right? So in the ground state, we can think of each energy level as like a container. So we have like 3 plastic containers on top of each other. And so we have 2 like plastic balls on the bottom container. And then 1 in the middle and 0 on top, right? And so the one that has the one that is lowest and has a plastic ball in it is going to be the HOMO, right? So the highest one that has a plastic ball is the HOMO. And in this case, we can think of the electron as the plastic ball. So the highest one with an electron would be pi 2. And that's why we call it the HOMO. And so the LUMO is going to be the lowest container that has nothing in it, that's empty. So pi 3 will be the lowest one, or in this case, the only one that doesn't have any plastic balls in it, right? And so we already named these containers. They already have like a cute little label that says HOMO and LUMO on it, right? But sometimes if a kid gets excited, they pick up one of the balls and put it in the higher box, right? So that doesn't mean that the box changed. The box itself still has the same label. Nothing is different about it. But what changed is the ball. And so if you come along and you see the ball in the wrong container, you're just going to pick it up and put it back. So that's why the HOMO and LUMO actually don't change between ground and excited. You're welcome. I used to work in a preschool, so every time I don't get something, I put it into like a children's reference. But yeah, so now we're going to go up to the table, and please don't forget, we're doing this last one now, and then we're going to go back to the radical. So please tell me, rapid fire, what is the number of atomic orbitals? Cool. What is the number of molecular orbitals? Cool. Pi electrons. 3. Sweet. How many bonding molecular orbitals do we have? Cool. How many antibonding? 1. How many non-bonding? And again, 1. Sweet. So is there going to be any difference so far between ground and excited states? No. So this will be 3, 3, 3, 1, 1, 1. Okay. So now, in the ground state, I want you guys to put in the chat the answers all at once, just separate by comma. How many electrons in the bonding orbitals, antibonding, and then non-bonding? And I'll give it a second. While you guys do that, someone asked, how is there a 1 antibonding orbital? So if we go back to the diagram, since we have 1 bonding and 1, since we have 3 energy levels, and we know that one of them is going to be bonding. There has to be one that's the flip, that's anti-bonding. They have to be equal in number, and so that's why, again, there's one non-bonding in the middle. Cool. And so people are saying for the ground state, it'll be 2, 0, 1. That is absolutely correct. And so how about in the excited state? Exactly. So the last two numbers are going to flip. So now there's 1 in the antibonding and 0 in the non-bonding. Cool. So for the ground state, how many electrons are in the HOMO? Ooh, we have a split. Okay, most people are saying 1. So exactly. This one is different from the rest because since there are only 3 electrons, there's one lonely one in the HOMO. But as always, how many will there be in the ground state of the LUMO? 0. Sweet. And again, for the excited state, how many in the HOMO? 0. How many in the LUMO? 1. Perfect. You guys are already masters at this. So we're going to go through the anion real quick because it seems like you guys are really getting the hang of it. And my pens are in the way here. Cool. So now the only difference as far as the picture goes is that we have 2 electrons in this orbital. And usually people draw it like that, but there's not enough space because I didn't draw it big enough. So I'm going to do it like this. Doesn't really matter. And someone asked a question. I just want to draw this out really quick and then I will answer it. I promise I won't ignore you. So the only thing that's changing is the number of electrons. We still have 2 atomic orbitals, 2 molecular, but now we have 4 electrons. And so now the naming of all of these is still going to be exactly the same because the number of orbitals has not changed. The only thing that changes between the radical and the anion is now we have 1 extra electron in pi 2. And so let me draw the star for antibonding before I forget. And so someone had asked, why would it be 0 and 1 for the excited state? So let's go back up real quick. So in the excited state, the 1 electron from the HOMO jumps up to the LUMO. So the HOMO is left with 0, and now that 1 electron that was in the HOMO is now in the LUMO orbital. Cool. So in the excited state, this bottom orbital is going to stay the same. 1 electron is going to stay here, and 1 is going to jump up here. And so we can call this the HOMO still, and this one the LUMO. Oh, someone corrected me, and thank you. I just wrote the wrong number. So for the number of atomic and molecular orbitals, it's 3, not 2. I just made a mistake. And I drew this one out kind of fast. Does anyone have any questions about why I put the electrons where I did, or why I named it the way I did? No? Okay, cool. So super quick, let's go back up and fill out the table. So you guys know by now that we have 3, 3, but we have 4 electrons, and then we have 1, 1, 1, and we already know that that's not going to change. But I want you guys to tell me how many bonding, antibonding, and non-bonding orbitals are there in the ground state. Cool. So as you guys said, there are 2, 0, and 2 because the antibonding is empty and the other 2 are full. So what about in the excited state? Cool, exactly. So 2, 1, 1, because one of the electrons jumped up to the antibonding orbital. And so then how many electrons are in the HOMO of the ground state? Yes, 2, 0. And then it goes to 1, 1 in the excited state because one of these 2 electrons jumps up here into the LUMO. And it just occurred to me that I forgot to send the attendance sheet, or the attendance thingy. So I'm sending that in the chat while we wrap up. So I'm going to zoom out. It might be kind of small, but I want you guys to be able to take their screenshots and everything. So basically, we covered all of the examples that he could possibly ask you on the exam because, sorry, I phrased that really weird because I was reading the chat at the same time. So someone asked in the chat, how come for the radical one, the energy jumps from non-bonding to antibonding? And the reason for that is it's always going to just jump 1 up. So in the excited state, the highest electron is just going to jump up 1 more energy level. And since there were no other electrons here, it would be all alone on the antibonding orbital. Versus here, since there are 2 electrons, it would jump up and there would be 1 on pi 3 and 1 still in pi 2. Does that make sense-ish? Okay, cool. And then someone said, how will he ask this on the exam? That's how we're going to summarize. I hit myself in the face. That's how we're going to summarize the session, basically. So the way he can ask you this is essentially just what we covered in the table. So he'll say, in the allylic radical, how many electrons are in the HOMO, in the ground state? Or in the excited state of 1,3-butadiene, how many molecular orbitals are there? Things like that, right? So what you have to be able to do is not draw this whole thing out, because honestly, if you sit here and draw this entire thing out for one question on the exam, you will probably not finish. So what I want you guys to do instead is practice this a couple times, draw it out, and just understand the idea, right? And then on the exam, you don't have to draw like this whole thing out. You don't have to draw like all this stuff. Just be able to, like, if you need to, recognize that these 3, the cation, anion, and radical, have 3 molecular orbitals, and the diene has 4. And then just be able to put the electrons in their appropriate energy level if you do need to draw it out. That being said, there are a couple trends that I want you guys to notice because that will make everything a lot faster. So if he ever asks you for the number of electrons in the ground state of the LUMO, the answer, no matter what molecule is always what? 0, exactly. And I'll repeat that. So no matter what molecule he asks for, if he says how many electrons are in the LUMO in the ground state, it is always 0. That's the whole definition of the LUMO. It's always 0. Another thing he will ask is in the excited state, how many electrons are in the LUMO? The answer is always going to be what? 1, exactly, because only 1 electron is ever going to jump up. Sweet. Another thing he could ask you is how many electrons are in the antibonding at the ground state. Awesome. Again, it's always going to be 0 because that's essentially the definition of the antibonding orbital. Cool. So how many electrons are going to be moved when you excite a molecule? Exactly. No matter what molecule it is, what you do to it, it's only ever going to be 1. So that is pretty much it for molecular orbital theory. I'm not going to lie to you guys. You did amazing today. And maybe that's just because I can't see you in person and people are afraid to ask their questions. Don't be. I don't bite, I promise. But you guys got it so fast. Usually I have to spend a whole session and then usually a second session on this. But it seems like you guys are doing really well, so I'm really proud of you. Thank you for participating so much. You guys did awesome. If you have any questions, as always, please feel free to ask away, either now or in an email or whatever. Yeah, I know I've been a little bit bad with my email this week because a lot of people sent me really nice emails, and I appreciate it a lot. I did read them. I just haven't had a chance to respond to them. And then someone said, can I ask the last 2 questions again? Yes, in a second. And then someone asked, is this the end of chapter 13? No, we have one more thing in chapter 13 that we will cover either on Friday or Monday, depending on what you guys want and how quickly we get through the other thing I wanted to cover. But we have something called Diels-Alder, which is this stuff right here. So that's what we're going to cover later. That's the end of chapter 13. And I believe the last 2 questions I asked were oh yes, how many electrons are in the antibonding orbital in the ground state? And so that would be 0. And then in the excited state, it's going to be 1. And then someone asked, should you know the specifics of how UV vis spec works? No. So all you really need to know for UV spec is what's written here. So essentially you just have to know that it tells you the level of conjugation, and it tells you that by the level of absorbance. And so the more conjugation, the longer wavelengths you absorb, and so the lower energy. And then someone said, how do you know which orbital is non-bonding if it's a cation on a butadiene instead of the allylic carbocation? So you wouldn't have a non-bonding. You're only going to have non-bonding when you have an odd number of orbitals. So if you have an even number of orbitals, the number of bonding and antibonding will always be equal. And so you won't have any non-bonding. But then let's say you have 3 or 5 or 7 or whatever number of orbitals, you will have as many non-bondings as you need to cushion the space between bonding and antibonding. And if that doesn't make sense, like let's say you had 5, right? I'm just going to draw it here. 1, 2, 3, 4, 5, right? So this would be bonding, bonding, antibonding, antibonding. And you have 1 in the middle left over, so that would be non-bonding. Jesus, someone scared me. I'm sorry. And so, yeah, his practice problems don't really have anything on molecular orbital theory, which is really annoying. But I promise, in my experience, he's never asked anything outside of what we covered on these 2 pages. So if you know those, you should be good. And then I'll scroll down in case anyone wants to like take a picture or anything. Cool. So have a wonderful day. I'll stay for another minute. As always, I hope you guys have a great day, and I will see you next time.